Welcome to lecture 11 on structural analysis 2. In lecture 11, we are going to apply the slope deflection concept to solve continuous beam problems. So the specific outcome of this lecture is we are going to see the procedure to solve the continuous beam and we are going to apply that procedure to solve the continuous beam. So for this lecture, I have the reference material is from Structural Analysis Volume 1 by Dr. R. Vaidyanathan and Dr. P. Perumal from page number 50 to 53. So the first topic is continuous beam. What is the concept behind the continuous beam? So the continuous beam is a statically indeterminate beam. So I think so I have already explained in the previous lecture that what is the difference between determinate and indeterminate. Determinate means we can solve the problem using the equilibrium equation sigma h equal to 0, sigma v equal to 0 and sigma m equal to 0. If it is indeterminate, then we need some more equations to solve the problem. So here the continuous beam must satisfy these two conditions, that is first one is geometrical condition and second one is statical equilibrium. So geometrical condition is nothing but it need to satisfy the slope deflection equation. Statical equilibrium is nothing but the algebraic sum of moments acting at a joint, that is the moment at some joint should be equal to 0. So the continuous beam need to satisfy these two conditions, then only we can solve that continuous beam. So next one is procedure to solve the continuous beam. So we need to treat the each span as continuous beam and we need to calculate the fixed end moments. Next we need to express all the end moments as fixed end moments and joints rotations by using slope deflection equation. That is, it is nothing but if you see this is the equation which we have already seen, this MFAB. This MFAB is nothing but the fixed end moment and this theta A and theta B is nothing but the joint rotations and this delta is nothing but the slip or the deflection, that is the sinking of the supports. So we need to write this expression in the write the each and every member in this expression. Next we need to write the equilibrium equation for individual joints. So while solving the problem you will understand what this mean by this step. Next we need to calculate the rotation, that is theta A and theta B in every support and we need to substitute this theta A and theta B in the equation and we need to calculate the final end moments. And after calculating the final end moments, we need to draw the shear force and bending moment diagram. So this is the procedure to calculate the continuous beam. Next we are going to solve a problem. So this is the problem based on the slope deflection method. Analyze the continuous beam loaded as shown below by slope deflection method and sketch the bending moment diagram. So they have given a beam which consists of three span, that is span AB is 4 meters, span BC is 6 meter and span CD is 4 meter. So we need to solve this problem by using slope deflection method and we need to draw the bending moment diagram. So we will see it in the board.
Here if you see I have drawn the beam drawing which I have shown in the PPT. Now we are going to solve the problem. So what is the first step? First we need to calculate the fixed end moments. As I have already explained in the procedure for continuous beam. First we need to calculate the fixed end moments. So before that they have given the condition that 2IAB equal to IBC equal to 2ICD equal to 2I. That is they have given the stiffness. Stiffness of the member is IAB is equal to 2IAB is equal to 2 times I. So we can take it as IAB and ICD equal to I and IBC equal to 2I. So this is the given data. Next we are going to solve the first step. What is the first step? First step is nothing but the fixed end moments. So we need to calculate the fixed end moments. Nothing but moment means what is the moment acting in the element due to the load. Fixed end moments means we need to consider the ends as fixed and we need to calculate the moment, that is the end moment. So that is will be called as fixed end moment. So first we are going to calculate the member AB. So if you take member AB, it is like it will be, we need to consider it as a fixed support. So it is carrying a UDL load. So the bending moment will be like this. So here if you see a moment will act like this and here if you see a moment will act like this. So this moment at this point the moment is acting in the anti-clockwise direction. So we are taking it as minus. So as you have already studied for fixed end moment, the formula to calculate the for a UDL load with fixed condition, we can calculate using the formula WL square by 12. So since it is in anti-clockwise direction, we have already assumed in sign conventions that if it is in anti-clockwise, then it is negative, and if it is in clockwise, it is positive. So since it is in anti-clockwise direction, so I have taken minus here. WL square by 12, you know the formula. W is nothing but 20 kilonewton per meter and L is nothing but 4 meters. So substituting, we are getting 26.67 kilonewton meter. That is the end moment, fixed end moment at A. Next we are going to calculate for BA, means at B. BA represent the member AB and first letter B represent the at B the fixed end moment. So if you see at B, it is clockwise direction. So we are taking it as WL square by 12 positive. So this is the moment. Next what we are going to, we are going for BC section. That is, if you take BC section, consider it as fixed end. So we are having two loads. So this is nothing but, if you take this, this is A1 and this is B1. So what we are going to, first we are going to consider the first force, that is 1. So that is A1, B1. Next if we are going to consider the second force, then this will be the A2 and this will be your B2. So first we need to take the first which load we are going to consider. So first load means A1, next distance is B1. Second load means A2, B2. So this is the difference. If you see in formula, WA1 B1 square divided by L square plus WA2 B2 square by L square. So if you see here, if a point load is given, then we need to use this formula. Generally, if I give a point load at the center, then we can use the formula WL by 2 like that. So since they have given it like this, that is 2 point loads acting at 2 different distances, not at the center, then we need to use this formula to calculate the fixed end moment. So if you see here it will create an anti-clockwise moment. So it will create a moment like this. Here if you see, it will create a moment like this. So if you see, this is in anti-clockwise direction, so we are taking minus here. So by substituting the value, A1 is nothing but, here if you see, A1 is nothing but 2 and B1 is nothing but 4. So 2 into 4 square by L square, L is nothing but 6. We are substituting 6 square plus 80 into this 80, sorry. Next we are going for A2, second force, that is 2 here. So 80 into A2 is nothing but 4, this point, this distance is 4 and B2 is 2. So 2 square, by substituting we are getting minus 106.67 kilonewton meter. Next for CB, at C, what is the moment at C? So we are going for WA1 square B1 divided by L1 square, same formula we are repeating, but here the sign changes. So this is, since it is in clockwise direction, so it is positive. So by substituting we are getting 106.67. Next what we are going to take, we are going to take the span or element CD. So if you take CD, it is having a UDL load. So if it is an UDL load, you know that at the left hand side we will have the anti-clockwise direction. So I am using the term minus WL square by 12. By substituting we are getting 20 kilonewton meter, minus 20 kilonewton meter. And at the right hand side, that is at D, we are having the positive moment WL square by 12. So we are getting 20 kilonewton. Remember, we are going to calculate the end moments at A, at B, C and D. So if you take A, means it is useful or it is only in the member AB. But if you see the join B and join C, it is included in both members, that is member AB and member BC, it is included in both the members. So only we are having 2 moment at B and 2 moment at C. Generally we know that if 2 joins, that is if a point is between 2 members, then at this join both the members will have equal and opposite moment. Then only we can solve the problem. So while solving the problem, you will understand that concept. So this is the first step, fixed end moment. Next step which we need to calculate the slope deflection equation. So second step is slope deflection equation. So next what we need to calculate the slope deflection equation or write the slope deflection equation. So first we are going to take the member AB. So I am writing first at A. So MAB equal to, we know the formula, M of AB plus 4EA theta A by L plus 2EA theta B by L plus 6EA delta divided by L square. So if you see here, this M of AB is nothing but the fixed end moment and this 2 two terms, theta A and theta B. These two terms is nothing but the rotation at the point A, and this point is the sinking. So how much a point is sinking? So by combining this, we can write the slope deflection equation. So by substituting the values for this equation, so we know that already we have calculated MFVAB equal to minus 26.67, and if you see here, remember the fixed end condition we will use only to calculate. While calculating the fixed end moments only, we will calculate all the supports are fixed. But while solving the slope deflection equation, we will consider what is the actual support at that point. So we will follow the actual support while calculating the slope deflection equation. So here if you see at A we are having fixed support. So we know that in fixed support there will be no rotation. If you take a fixed support and if you apply a load, then the rotation will be like this. So if you take the rotation of the support, it will be 0. So only we have taken 0 here. Next, if you take theta B, it is a hinged support. So it will allow rotation. So we are taking 2A theta B by 4. But that is L is nothing but the 4 plus 0, because the support is not sinking. So the sinking will also be 0. So we have taken this. By simplifying, we will get the equation. Next what we need to take the BA, that is in member AB we are having two moments, that is at MA one moment and at MB one moment. So we are going for MBA. MBA equal to M of BA plus 4E theta B by L. Remember, at what point we are calculating the moment, at that point we will have 4 times EA theta B by L, and at the other end, that is if you take the member AB, if you are calculating for B, then at member A we will have half of that impact, that is 2EA theta A by L plus 6EA delta divided by L square. So if you take the theta A, as we already mentioned that at theta A the rotation is 0, so it is 0, and 6EA delta. So this since there is no sinking of support, so it is also 0. So by simplifying, we are getting MBA equal to 26.67 plus EA theta B. Next we need to take the member BC and we need to calculate for member CD. So next we are going to calculate for the member BC. That is, first we are going to calculate the moment at B in member BC. MBC equal to, we know the formula, M of BC plus 4EA theta B by L plus 2EA theta C by L plus 6EA delta divided by L square. So we have calculated M of BC, that is the fixed end moment. It is nothing but minus 106.67 plus, here if you see both B and C is hinged support, so it will allow rotation. So we have both theta B and theta C. So for EA, here if you see IBC equal to 2I, so I have substituted 2I theta B by 6 plus 2E into 2I theta C by 6. Since we have rotation at both B and C, we are having theta B and theta C. So by solving, we are getting this equation, minus 106.67 plus 4EA theta B by 3 plus 2EA theta C by 3. So next we need to calculate the moment at C in member BC. So MCB equal to M of CB plus 4EA theta C by L plus 2EA theta B by L plus 6EA delta divided by L square. So this is the formula to calculate the moment at C. So by substituting the values, we are getting this equation. So next what we need to, we have calculated for member AB moment at A and moment at B in member AB and moment at B and moment at C in member BC. Next we need to calculate moment at C and moment at D in member CD.